let's walk through this problem together. And the ultimate result is trying to figure out what the area under a curve represents. So first thing, we're just going to take the area. And a lot of you remembered that the area of a rectangle is base times height or length times width, right? Easy peasy. Multiply it together. So we've got a base of 4 seconds and a height of 5 meters per second. There was a big argument over, wait, do the seconds cancel or do they multiply together? This is kind of tricky. So in order to think about this, the seconds by itself is in the numerator. The seconds here is in the denominator. So you can make this a fraction if you put it over 1. And then the seconds in the numerator does cancel with the seconds in the denominator. So you have it right. And you end up with 20 meters. For question number 2, we have a different shape. Out to 4 seconds, we hit a height of 8 meters per second. And this isn't a rectangle, but it's half of a rectangle. It's a triangle. So that's half of the base times the height, which is half of 8 meters per second. I'm going to include the units, even though you don't have to in your work, times 4 seconds. All right, if we simplify this down, we do end up with 16, but the unit should be what? Meters squared? Just meters. So we've got 2 values that are in meters. What does that tell us about what this value, what the area under velocity time graph represents? What do you think? Position. So if I've got an object, let's look at the simple one. This is a basic object that's moving 5 meters per second. Someone's traveling 5 meters per second, and they're traveling 5 meters per second for 4 seconds. Would it give me just my position? I mean, I guess it would if I started at 0, but what do you think? Ben? The distance traveled, another good suggestion. We have 2 vocabulary words. One is distance, no direction, just the total distance traveled, and the other one is
would it be like the maximum distance that it goes?
Not maximum. Well, I mean, depending on how you interpret it, but it's a specific vocabulary word I'm looking for. James?
Disposition.
Which one?
Disposition.
Not disposition, but I think you have the right idea. Well, it starts with a dis. Displacement. Yep, displacement. So displacement is the change in position. And Rachel is right. If we start at a position of 0, on a velocity time graph, do we know what the starting position is? If I had to draw a position time graph from this, would I know what the starting position is? It could be anywhere. You could draw your position time graph anywhere on your axis. So really, all we know is the change in position from start to finish, which we call the displacement. So what we've got is the area under a velocity time graph curve gives us displacement, and it represents the change in position, change in position, which is represented by a delta x, delta meaning change. So when you write out an equation like this, you're actually going to do this in your worksheet today, but I'm going to walk you through this anyway, and you can just literally copy it down, is the change in position, delta x, is equal to the base, which we established is time, because the base is my x-axis, times velocity. So I'm going to call it v times t. Change in position is another way of saying position final minus position initial equals v times t. And then last but not least, you've got this in your physics helper. If I just added this initial position to both sides, I have an equation in my physics helper, which is x final equals velocity times time plus x initial. This is literally in your physics helper. When my light turns on, it is right here. So x final equals velocity times time plus x initial. This change in velocity that we started off with is also in your physics helper. Change in position equals velocity times time. So we came up with those two equations just by taking the area under the curve. All right, next, we are going to do a little review. So I'm going to use the same graphs that we used up here, but this time we're going to take these velocity graphs and we're going to draw position time graphs out of them. Position and acceleration, actually. So let me pull this back over. This is really what your quiz is going to be on. So let me make this a little easier to read. I've got a constant velocity graph that shows a nice horizontal line. If I asked you on your quiz to draw a position time graph for this velocity time graph, how would you draw that? Alexa. A positive slope, but it needs to be a positive line with a positive slope. First thing you want to know about a velocity time graph is it tells you the direction. If it's on the positive side of the axis, it must be moving in the positive direction, which means I could start it anywhere, right? Most students are going to start at 0. Let's say it starts here. As long as it moves forward at a positive constant velocity, that is going to be a position time graph for problem number 1. I didn't draw it to accurate values, but I want to see a positive slope here. Now what I want to do is find the acceleration graph for this. And I'm telling you, it is easier to go from velocity to acceleration rather than position to acceleration. Ashley, what do I need to do?
Wouldn't it just be a straight line on like the time line?
On the time axis. How did you figure that out? What did you do to this graph to get this graph?
I just kind of remembered being taught us last time.
Just memorized it, Kate? There's no acceleration here. The velocity stays constant, and no change in velocity means no acceleration. What's another way to look at it, though? Alexa? Horizontal line has a slope of 0, which means my acceleration is a flat line at 0. Okay, let's look at something that actually does have a slope. So I want to find the acceleration. We're skipping the position graph first. I want to jump to acceleration. What would the acceleration graph look of a velocity time graph that is not a horizontal line? What would that look like? Kaya, did you have an answer?
Straight line above the x-axis.
A straight line on the positive side of my time axis. I want to make sure that I show a positive slope means a positive constant acceleration. And a 0 slope has a 0 horizontal acceleration. What about my position time graph? This is the hard one. I have a velocity time graph here on the positive side of the velocity axis. How would my position time graph look for this one? Let me have Ashley.
Wouldn't it be like the upwards curve like that?
So I have to go in the positive direction. And I have to start slow, which means my position doesn't change much in the beginning. And then it starts to speed up, which means I have a steeper slope toward the end. Really good. Any questions? All right. I am literally going to pull questions from worksheet 2. So take a look at worksheet 2. I can go over any questions you have if you want to Check in with your neighbors. For those of you who didn't correct them, it'll be a good idea to check in with your neighbors, or if you want to just come up and ask a few questions before we take the quiz. I'll give you about a couple minutes, 2 minutes, to look over this worksheet. Okay, let's go over our assignment for today is worksheet 3. Worksheet 3 is actually pretty short, and it's fairly easy. So I want to go over kind of these steps with you. And the last part of this, we already did in class today. So over here where it says, use the appropriate mathematical model. When you're writing a mathematical model, you want to use the appropriate variable. So instead of base times height, you want to use velocity and time. So we did that for the warm-up. But there's a lot of important vocabulary that's used here, so I want to make sure to highlight those things. First of all, it says a scenario. You're going to have to graph the scenario, but one thing it tells you is it says assume the clock starts the instant you hit the brakes. So it tells you you're on cruise control for 25 meters per second. I don't want you to draw cruise control at 25 at the beginning of your graph. I want you to start your graph as soon as the brakes are hit. So 25 is where you start, and then you come to stop at 40. It is much easier to start with a velocity time graph because they give you velocity. So start with the middle graph. It doesn't label it for you, but velocity is the middle graph. And then from there, you can draw your acceleration graph, which comes after it. And then your position time graph, which comes first. But it's always easiest to go from velocity to acceleration. And then position's always the harder one. So I would do that last. Next, it defines qualitative graphing versus quantitative graphing. Qualitative means no number values. So no number values. Whereas quantitative, quantity means add your number values. You're literally going to take this graph and you're going to put units in your axis here. Here, no units, no values. And then same with acceleration. And it doesn't even have you redo the position time graph because what did I say about velocity? Can you find the initial position from velocity? No. The other thing it tells you to do is graphically represent displacement. We just stated area under the curve is your displacement. If you graphically represent it, it means shade it in. So you can grab some color pencils, you can grab a highlighter, but I want you to shade that displacement on your graph. And then you're going to calculate it. And then you're going to draw your acceleration graph. You only have 2 problems, really. There's a bunch of little parts for each question, but your second question is the same thing. It says, here's your scenario. You're on a stretch of highway. For 0.5 seconds or half a second, you're going 30 meters. And then the following 3.5 seconds later, keep in mind this says 3.5 seconds later, you come to a stop. Again, quantitative graph, graphical representation means shading, and then you're going to solve it here, but it wants you to use your mathematical model to solve the exact same thing down here. You should be able to finish it in like 15, 20 minutes. I'm going to save the last few minutes for whiteboarding. And then, yes, we are going to take another quiz on this next class. We've got a test coming up next week, so I want to quiz you as much as possible so that you can learn from your mistakes on the quiz and then get it right on the test. All right, go ahead and get in your groups. I will come around. If you have questions, shouldn't take too long to get through this worksheet. Pop through it together. We'll go over the answers. But I want everyone to look at the different versions we have up here. We have a position time graph moving upward. We have a position time graph moving downward with a kind of outward sort of motion and then a downward slope that comes down and out. So let's think about our scenario. Our scenario is a person who starts at 25 meters per second and slams on their brake. Of these three scenarios, first of all, let's think about direction. If I'm driving and then I slam on my brakes, what direction should I be going in? In the forward direction. So we want to make sure we start at 0, or actually you don't have to start at 0, but you want to make sure to move forward. So now we've got two position time graphs that are moving forward. This one and actually this one's not moving forward either. This one's moving backward, right? But we have two moving backward, but we also want to think about the motion. It's moving at 25 meters down to 0. So at a fast speed, down to a slow speed. This is fast speed, down to slow speed. It's just moving backward from fast to slow. So we want to make sure we're moving forward at a fast speed, and then we slow down. Does that make sense? This was part of your test. Or sorry, this was part of the quiz you just took. So hopefully we get a little better. Let me have you guys make sure if you did not do position time graph right, make sure to do your position time graph correctly. I'm going to have you graph the second question, so keep working. A big argument. Do you end your graph at 3.5 or do you end your graph at 4? Why 4? Numbers? Why 4? You because you start decelerating at 0.5 and 3.5 after that, it ends at 4 seconds. There is a big argument. It's a common mistake. So make sure that you keep that in mind if you're doing this problem, okay? Clean up your material.